Please let's welcome Ram.
Thank you. Thank you. Hello. Howdy. Hi. Thank you all for coming after the lunch talks. It's super hard act to follow, Hiram, John Seymour, Insanity Bit. So I'm just going to build and stand on the shoulders of these giants. And the way this talk is structured is my goal is not to get through these slides. I will kind of hope you will have a lot of opportunity to ask questions. And the second thing is even though I'm the one presenting, this work represents the corpus of 32 applied ML engineers in our group. So it's not just me who did all this work. So I want to make that clear. So, and Gabe is not here, but thank you, Gabe, for inviting again. So the first thing I want to talk about is how we think about the current state of security. Right? And if you think of the red team kill chain, this is something we're all familiar with. You've got, attacker doing some sort of reconnaissance, establishing some sort of persistence by compromising a service account. They move laterally and they exfiltrate data. We all know about this. So what we did was in 2012 when we were thinking about rejiggering the way our team thinks about security data science, we spoke to a lot of analysts. We spoke to a lot of blue team members, and we found out that they also have a discrete set of steps that they take to kind of attain their goal. So and this is what we call the blue team kill chain. So the blue team members, they kind of gather data sets, they author atomic detections, there's some sort of alerts that being written down, and then it comes to triaging, right? This is when they're all looking at multiple panes of glass and trying to see if there's which is the one that's sticking out like a sore thumb. And then once they find the alert, they gather context, they run their playbooks, and then they actually execute some sort of remediation or response procedures. And what we found is that if the length of the blue team kill chain is the same as that of the red team kill chain, it's awesome. You are playing the role of an arson investigator. The house is already burnt down, and you are now going to see what caused the burn for the house, which really doesn't add much value. So we asked a question for attack detection, can we pivot the conversation to attack disruption? And what that really means is that you're trying to play the role of a firefighter. The length of the blue team kill chain is now reduced. It's not the same size as the length of the red team kill chain. And can you disrupt the attacker, before she attains her goal? And that's what is going to be the theme for today's talk, is how can we disrupt attacks? How can we pivot the conversation from attack detection to attack disruption? Why can't we do that today, right? For us, the biggest roadblocks that we kept hearing again and again was, hey, there's too many false positives. There's so many, we get drowned in alerts, we're not able to get to the goal that we want to attain. And when we thought about this in context of our red team, blue team kill chain, what really happens when people say false positives is annoying is that the blue team member is not able to go beyond alerting. They get all these alerts, but they're not able to triage, they're not able to gather context, and therefore they're not able to execute on their $1 million playbooks that they have authored. So, being the bashful young folks that we all are, we were let's solve this using visualizations. Let's give them graphs. Let's give them some sort of pew pew graphs to kind of make it look awesome. So this is an alert from our automated accounts. This is when an automated service account kind of logs in interactively. It should never happen. And we just wanted to alert on this sort of anomaly. And we did what everybody else would do. We had dashboards, we had Power BI charts. And we basically said, hey, if you click on this, you should just see this graph and just go do your thing. And the problem with is in the context of Azure, there are API calls that are being made thousands of them in order of a second. So where all of this becomes instead of intelligent triaging, it's where do I find Waldo? And the second problem is that our red team members have shown again and again that attacks do not stick out like a sore thumb. If I'm not able to find like what is anomalous in thousands of API calls, there's no way I can expect like my analysts to do it. So the first thing that that we kind of had to come to terms with is the scale at which we operate in. So we see like 630 billion authentications per month. If I have a false positive rate, a modest one of 10%, that is still in the hundreds of billions ranges. So I need to kind of like think of methodologies that really shrink or operate at the scale at which the data that I'm seeing, and also at a much higher like false positive rate. So we started like thinking about had a couple of mind shifts, and this is the first like 5 minutes. I'm just going to walk you through the different mind shifts that our team had. And the first thing is like we wanted to focus on what we call like successful detections. So the x-axis is like sophistication of an algorithm. It could be basic or something like advanced. The security domain knowledge. Are you putting a lot of effort into it, or is it only little effort into like getting domain knowledge? And then the other side is the utility of those alerts. Given alert, is it actually useful or not? And if you were to do some sort of like basic outlier detection, this is like number of failed logons greater than like 2 times standard deviation. It's an outlier. It's a fairly straightforward method, and there isn't really much security domain knowledge that goes into it. And you should not expect a big utility in terms of like your rate of return, or that's what we found. So the immediate knee-jerk reaction is like, oh, let's bring in time series analysis. Let's really increase the complexity of our algorithm. And this is what I actually did right off the bat. Like, we had a look at weird times that people check in code into their system. And we just like built a very like regular like vanilla time series Holt Winters system to look at like failed logins when they're checking in code. But here's the deal: like the problem is that just blindly increasing the complexity only produces anomalies. So the way we think about that is like the way my system failed is. It works really well in the North America's region, but the concept of weekend in like the Middle East is extremely different. They have like in Israel, like the weekend is Friday, Saturday. So people are not checking in code actually check in code on Sunday because that's their Monday. So thinking of like just blindly increasing the complexity really does not give you much values. And what we think is a true goal is like successful detections, or security interesting alerts. And that's what you really want to strive for. So the second mind shift that we had is like, as data scientists, we have this like insane curiosity towards feedback, right? Hey, I'm producing an alert. Let me go talk to my analyst and let my analyst be like my mechanical Turk and, like reap off like the feedback that she provides to me. And it's kind of really sad because like that's really not an analyst's job. An analyst is there to kind of like secure the system and helping and just looking at them as like a proxy for mechanical Turks or vendors to get like your feedback was not useful for us. So what we did was we tried to tap into like the other assets that we have to get labels. So for instance, like bug bounties. We had like simple bug bounties like internally within Microsoft, and then soon outside when like we said, hey, if you were to come and attack Azure, you'd probably get like a monetary reward for that. And like red teams are another like great way for us to like get label data. My favorite one is actually like getting labels from other products, which I'll talk about in a case study going forward. The third thing is like understanding how the cloud is very different from on-premise setting. So in on-premise, like we all have this like really nice, comfy feeling of our network, of a private network. We exactly know the crown jewels, like Active Directory, and anytime like if your Active Directory is pwned, then you get keys to the kingdom. You could be like domain admin. But if you think in terms of the cloud, it's a little bit different. And it's a little bit same as well. So it's same in the sense that anything that you see on premise you will see like a cloud analog. So for instance, like you might see, you might have like on-premise SQL server to host your files. In the cloud, it's SQL Azure. You might have like your domain controller, which would be like Azure Active Directory. So there are a lot of analogs, like servers become services. But it's also very inherently different. The whole point about the cloud is that there is no single point of failure. So like what are the crown jewels of Azure? What are the crown jewels of your cloud? So asking this question and like really talking with our red team and our blue team kind of helped us identify, oh, okay, so the LSAS over here is kind of like the key vault in the cloud, or like protecting storage accounts is important because like, hey, protecting SQL Server is important. So we try to like make these analogs, and this was like done by our red team to help us. Like when we took like the knowledge that we had on premise and translated that to on the cloud. So things like, the attacker, her goal on premise, she might be like, I want to be domain admin. But on the cloud, it really translates very nicely into like becoming subscription admin. Or like things like pass the hash on premise is like a credential pivot, wherein like, an attacker, she might like pwn a subscription, she might get like her certificates and kind of like, pass those certificates and authenticate. So we try to do these like translations to help us guide like intelligent cloud security detection methodologies. The fourth one is like we want to solve for classes of attacks. We kind of have a 33-member like data science team, and we still have an extremely healthy backlog of things to get done every semester. And what this informed us is like, there's always going to be more security scenarios to solve than the resources that you have at hand. And this is an important insight because if you're going to have a unique custom solution for every security scenario that your management asks you to solve, it's going to be hard. And this is like traditional machine learning, wherein like every task gets its own learning system. What you really want to pivot to is trying to learn from related tasks. If you've solved like detecting geologin anomalies in Azure Active Directory logs, try to use that methodology, and we will see how it transfers to detecting unusual SSH logins. So this kind of like helped us to keep our backlog and try to manage it in a healthy fashion. The last one, really want to embrace empathy. I know this sounds a little frou-frou, but there's one thing that's really helped us to build what I think is like solid ML detections is to think and talk to our security analysts. We put them front and center, and again, like we do not look at them as mechanical Turks. Like this is like a picture of what we call the grading fiesta. We host every bi-weekly, when every member of our team comes together and we grade a person's detection. And if we're not able to grade it, and if we're not able to like understand what the anomaly is, there's no way in hell like our analysts or like our customers are going to be able to do it. The second thing that we started doing is we really had like partner calls when we asked them like, hey, we're going to private preview, would you like to test it? So really getting that feedback from our customers really helped us to think like, okay, we are building solutions for them and we want to be able to help to them. So given these like 5 different things that I spoke about, I'm going to tell you, kind of ground them how we protect assets in the cloud, kind of like on the host, on the identity, and on the service level. So the remaining time is just going to be the case studies in each one of these areas. So I'm going to start off with the host and talk about like detecting like malicious PowerShell commands. So I don't have to say this out. PowerShell is like malicious usage of PowerShell is on the rise. I love the graph from Symantec. This is a nice like hockey stick. I think it was right after PowerSploit was kind of like released. And today we're going to specifically think about like PowerShell obfuscation. We're going to run through this really fast, right? This is just a very simple like PowerShell command to kind of like download malware from this like malicious website. But first off, I can escape the commands. I can then kind of like escape the characters within the command. I can even escape the arguments. I could put a pointer to the new object. And all of these does the same thing. And then I could basically escape everything. And this is like, you know, for classic Daniel Bohannon, who came and schooled us in like Blue Hat. So essentially, if you were to use all of these things, do the same thing, which is like, you know, go to the same website and get malware from them. And if you were to decode like PowerShell command lines, right, rules really don't work that well because like you have to write a regex for each one of them. And classical machine learning does not really work that well for us because like every command line is unique. There might be no discernible pattern. So what we tried to do was our previous approach actually used n-grams. It didn't use the cool kilograms talk that Hiram just spoke in, you know, in the last session, but we basically used like 6 grams, and our true positive rate was around 67%. And you know, we want to ask ourselves, can we do better? And our hypothesis was like, hey, deep learning methods are kind of like really efficient at capturing like semantic variations. Is it possible for us to use this in this particular problem domain? And the overview, you know, in the next couple of slides, what I'm going to show is like how we try to capture semantic relationships using embeddings, and how to use those embeddings to kind of classify those command lines. So quick kind of like preview of an embedding. So it's really popular in natural language processing. I think there was a fantastic talk yesterday on like embeddings and malware. I'm sure you know they probably do a much better job than the couple of slides I'm going to show you about. But essentially when somebody says embeddings, all you want to think is like taking words and converting them to vectors. And if you just look, the classic traditional approach would be like one-hot encoding, but really that doesn't kind of give you much because you lose semantic information. So one-hot encoding is just like, you know, if I see that word, put a 1, everything else in my vocabulary is a 0. It's an extremely sparse matrix. But embeddings, in the other words, are dense vectors. So the meaning of a word is captured in, say, like 4 bits of information, and it's kind of smeared across that 4 bits of information. And once you use like embeddings, essentially what it helps you do is it helps you capture these semantic relationships between words. This is like the classic like hello world of embeddings. You know, if you take the vector for the the vector representation of queen, and then you subtract from the vector representation of woman, and then you add the vector representation of man, you should be somewhere in the domain of like the vector representation of a king. And the reason why this works is because like, the meaning of a word can be inferred by the company that it keeps. And our goal is like, can we infer the meaning of a command by the company of the other command lines or the other commands next to it? So that's kind of like the problem we want to solve. And we use vir2vec. And essentially, like what you essentially get is like you're able to distinguish things that don't match. So for instance, like all of those are kind of like vanilla like Boolean variables, but that one is all the ones are literals, but that was a Boolean variable. You would be able to find that. All those are kind of like window styles, except bypass. You would be able to figure that out using contextual embedding. But the real power of contextual embedding is you can also learn linear relationships like the one that I showed you. So export CSV minus CSV plus HTML gives convert to HTML. So what does this give you other than the fact that we spent like probably a day, if I'm generous, coming up with these slides. The thing is, if you were to see in your training set, if you only see if you only see export CSV, CSV, and HTML, you can get convert to HTML. You do not have to see convert to HTML in your training set for you to realize, because you would be able to get that by the previous things. And that's where the discernible pattern, that's how we circumvent the discernible pattern of like the previous approach is when attacker, when she uses a command that we have not seen before, but we have a healthy corpus of training data, we're able to infer what's kind of like not seen. And this is basically the data set that we have. We get benign scripts from what our own environment has, but we also take from the PowerShell gallery, and we tokenize them. We get 1.4 million distinct tokens. And essentially, we learn the embeddings from the unlabeled scripts, and we have a very, very tiny corpus of labeled scripts. And that is essentially what goes into our convolutional neural net for classifying, for training our model. So I'll show you very fast. I'm going to pray to a lot of folks now, especially John Ho's right there. So this is what an embedding looks like using TensorFlow. So essentially, what we've taken 10,000 command lines, and we've projected them on 3 principal components. And imagine that an attacker, you've seen, invoke web request in your training set, but an attacker, she now uses IWR, same reference to invoke web request. So if I can search for IWR, something that I've not seen before, in my embeddings, I'm not sure if you can see it, but the first one is invoke web request. So that's essentially trying to circumvent, again, the problem of hey, I've not seen this before, so I'm just going to check my embeddings, see the nearest one to my embedding, because just like how a word is a word by the company that it keeps, a command is a command by the company that it keeps, IWR is most likely invoke web request. So I'm going to project back to this. And this is kind of our results that we have. First off, the model's been trained multiple times per day, and I've got and the most important thing is its classification is completed in the order of seconds, as opposed to again coming back to lengthening the blue team, shortening the blue team kill chain, and we got a really a good hefty false positive increase in true positive rates by keeping the same false positive rate, which I think is a good way to show our management why our team should exist, because we've not made the system worse. If anything, we're able to catch more attacks. We'll also put a link to the paper on archive, and I'll be distributing the slides anyway. Please feel free to the code's also published on GitHub. Please feel free to play with it. So the second thing, case study, I'm going to still be in the realm of the host, is trying to detect compromised virtual machines. So our previous approach kind of used rules and heuristics. So the problem at hand is a virtual machine compromised or not? And our true positive rate was 55%, marginally better than tossing a coin and deciding if a VM is compromised. So we obviously wanted to do better. And the solution that we gravitated towards was kind of leveraging the spam information from Office 365 alongside the NetFlow data from Azure. And essentially our hypothesis is, if a VM is sending spam, it's most likely compromised. And we know that the VM is sending spam because we get the spam labels from Office 365. So we basically, they maintain a corpus of information that says this IP is been sending out spam, and if we see traffic from a particular virtual machine from that IP address, we kind of use that as label data for spam. And there's a lot of good reasons why network data is good for detections. You, first of all, don't have to do any sort of installations. It comes free. There's no overload on the customers. And essentially it's OS independent, which is important in Azure, where there's a good healthy mix of OSs that's actually running on top of it. And some of the features that we extract from IPFix, by the way, is kind of like NetFlow. We extract from the NetFlow data. We look at the ports with traffic, number of connections, which TCP flags exist. So those are kind of like our features. That's kind of like essentially the columns of our data set. And like I said, spam tags come from building 34 in Redmond. So this is what the training data looks like. We got the handful of spam labeled data, and we got like benign IP fixed data. And then we run it through like our random forest model. And then, given a new case, given like a previously unseen like net flow data, if we were to run it through our ensembles, we make a judgment, is this possible or not? So I'm going to just I love talking about ensembles because it's my favorite. And this is essentially like what it would look like. So imagine like all the positive examples are like benign traffic, and like negative examples are like malicious traffic. And now you have to find represented in 2 dimensions. You have to find like a hyperplane that kind of like divides them into both. But it's not really possible because there's no one single line that will cleanly divide both of them. So you need something with a nonlinear decision surface. And the first time is like you would learn with one learner. You would do some classification, and you'll see like this learner kind of like classifies, gets some of these positive ones. It calls it malicious. So you now identify those, you upweight them, and the next iteration for anything that you have downweighted, anything that you've got correct, you downweight, and anything that you've gotten wrong, you upweight, because you want to think of like a really bad like teacher. She only looks at like the bad things that you do, and she wants you to get that correct. And then you upweight those, and then your second learner gets those correct, but at the risk of getting the others wrong. And then you do one more layer, so you boost those things now. And essentially you iterate with different rounds of boosting, and the final result is a combination of like multiple learners, and you get this like nice decision surface. So the reason why we kind of like use ensembles is that it's ridiculously fast. It actually was used in Connect for like post estimation. So again, you want to like think about shortening the blue team kill chain. So we are able to like classify in the order of seconds. And our training is relatively fast. We're able to get we run it actually multiple times per day, and it's completed within the order of minutes. And we got a 26-point improvement just by using like an out-of-the-box ensemble method. And this is also a good lesson for us to kind of keep in mind. If there's an easy solution, please take it. There's no reason for you to kind of look at fancier methods. In fact, we actually start off with logistic regression. We could have had a high school student come and solve this problem for us. But the important thing to keep in mind is if you can kind of optimize for a business metric, which is hey, I want to be able to detect attacks faster. And out of the box, most of the time, out of the box solutions are pretty good at scalability. The third case study is going to be identity focused. So we saw 2 case studies that were focused on host. Now I'm going to talk about a case study focused on identity. So, one of the things we like to think about is the ML journey. And this is something I got a lot of help with my product marketing team, but they did a really good job. So on one hand, you've got folks who really don't have much machine learning powerhouses, right? But they still have the the yearn to kind of I want to put machine learning. Probably their board wants them to do machine learning. But the unfortunate truth is getting security data scientists is like finding a unicorn, right? Because they command NFL-style salaries. They want to be able to you can't have a big, enormous team. So our problem statement was empower businesses who are not able to have security data scientists to do machine learning. Specifically, you have a solution to detect anomalous Azure Active Directory logins. Open that model up for anybody to detect anomalous logins for their problem domain. It could be SSH, it could be Linux logins, doesn't matter. So that was the problem at hand, to kind of help those folks who don't have any ML investments. We're not talking about you guys who are like have like advanced ML investments, for people who have no ML investments, taking the things that we have built and opening it up to them so they can build on top of that. So in the use case, the challenge that was presented to us was like anomalous login. This is the classic time travel. Like Rom lives and works in Redmond. At minute 1 he logs in from Redmond, and minute 2 he logs in from Hungary. It's not possible. So we actually have solved this problem in Azure Active Directory, and the thing was like, can we take this and open this up so that other people can build on top of this for their own login space? There was no previous approach, but our solution was like, can we reuse what we've already built without like building a more generic model? So I'll first like explain what we have, and then I'll tell you like what modifications we did. So this is like the geologin anomaly detection. This is in production and identity protection. So it has basically like 3 straightforward steps. First off, we capture like 45-day windows of like your login data. And essentially, like, user is kind of like mapped to some sort of like ISPs and some sort of like, use like a geolocation service to look it up. Excuse me. So what essentially, if you look, like user 1 is kind of like in the Bellevue, in the Washington area, and user 4 seems to be in the Massachusetts area. But we don't know that yet. So the first, once we capture this like login data, we calculate like user-user similarity metrics. So using like custom like mappings. So all this does is that it helps you to find like how users are similar against each others. And this, like you can imagine, and it's done within the context of a tenant, by the way. It's not done globally. But it's an extremely sparse matrix in the sense that users who tend to kind of like have the same sort of like login patterns are kind of like have, the end goal should be to have like same similarity mappings. And this is kind of interesting because like when you think of geologin anomaly detection, it trips a lot of like vanilla systems because people travel, people kind of like use like VPNs or proxies. So the goal was, hey, if we wanted to take this in the context of a peer. So if my manager travels to Israel, because like we have a team there, then when I log into, if there's a login for me from Israel, there should be like a small like finite chance occurred to it. And this is exactly what the second step does. And the third step is like we basically run random walk with restarts on this similarity matrix, and this kind of like gives us a reachability score given like at a point in time what are the different locations a person's login history should be. So this is great in terms of like at Microsoft scale, but but to open it up we had a lot of problems. First off, it's extremely heavyweight in the sense that it's compute intensive and it needs like, I showed you like, it needs like training data in the order of billions. Whereas like if, not many organizations might have like hundreds of billions logins that they see every month. And it also uses handcrafted features, which means it really doesn't transfer that well to like other domains. And it's really hard for us. We found it very challenging to kind of like add new data patterns that are very specific to different log sources. So what we ended up doing was we used recurrent neural nets. It's like, if anybody hasn't said the word deep learning yet, I feel I should get the pity brownie. It's purpose, but we try to do it thoughtfully though. The reasons why we went the LSTM route is, first of all, LSTMs are great in terms of like they're built for like sequential data. And if you're trying to detect like login anomalies, nothing works better than this. And it also deals well with scale invariance. It's a fancy way of saying that, if when people log in, they don't log in with like specific intervals. Actually, that'd be really weird if I just log in every day at 8 a.m. and log off at 5 p.m. So when you have this like invariant scale, like LSTMs work really well. And essentially what we did was we took our bulky like geologin anomaly detection system. We said, you're bulky, we can't like transfer you. So we essentially used that as a teacher to get labels from our SSH logins. And LSTMs have really good capacity to kind of mimic. That's one like interpretation of it. And we used that we use the labels from our bulky GLAD system, and we essentially extracted features like timestamp, users, and location that kind of like, if you look at the features that we use, it's really not specific to SSH logs. It could be used in network logs. It could be used in other types of log sources. So we try to look for like fields that were common across multiple log sources and use LSTM for it. And this is essentially what the data set looks like. You know, we get 2 weeks of login data per user, and we take those features and we essentially put them in sequence. And the task at hand is the login at, say, time t2, is that like malicious or is that benign? That's essentially what you want to do in the context of SSH logs. So you take like those sequence of like logins, and you know, there's the featureizer. That's when you extract like user, location, timestamp, and you can see it's a very actually pretty shallow like LSTM model. So we got 3 layers, and then you get an output for that particular login, whether if it's like malicious or benign. So if my login at T2, you know, is contingent on my login at T1, but also login at T3. So you know, if I log in generally from Redmond, but then I saw like a login to Malaysia, and then I see a login back from Redmond, you know, Malaysia kind of should stand out, and that's what this kind of the scoring phase does. So how does this look like in production? I feel like this is like something I wanted to again feel very passionate about. Essentially, what we do is that we built this in, we had to do this in near real time. So we use like a Databricks cluster. And we have like a high throughput event hub, which is like a Kafka-like service. So it's able to suck in billions of logins per minute. And essentially we get the state of where the user logs in. That's kind of stored in Azure Blob. So you know, for any time like I see like a user's login, I'd be able to like query like Azure Blob very fast and get in our production pipeline, and then it's written back to an event hub that customer can kind of consume in. So how does this kind of look like? First off, I want to say that this is still in private preview, which is a nice way of saying it's still in like a little bit of a research phase. So I do not have metrics to share for this, but that will change very fast. So the cool thing about LSTMs is there's so many people have worked on optimizing for scale and for throughput that essentially training only takes in the order of seconds. And if you run it on streaming mode, the mean time to detection is again in the order of seconds. Once again, we want to like really think about shortening the kill chain per se. And also like if you think about for this specific problem, logging in might be like the first vector for an attacker. So you know, you want to be really fast at blocking the login or trying to determine, but at the same time, you don't want to ire people out. You don't want to be the person like between what the person's trying to resource and them. So trying to keep this in the order of seconds was super important. It's something you'd find in like Azure Sentinel. So you know, given that, I'm going to talk last about like how we protect the service using the mindsets that we had. So our rallying cry soon became like, you know, we do not want analysts to triage incidents. We only want them to look at alerts, right? And now I have like 3 independent alerts. You know, I've got like one for anomalous DLL that's been loading, you know, some new process that started, and there's another like separate alert for some sort of large transfer from a SQL server. And it really doesn't tell a story, and you're just adding to the burden of triage to an analyst, right? And what we really wanted to see was, is there a way for us to extract, say, a story with these alerts that happen? Hey, in the context of a host, there was anomalous DLL, and there was a process, and here's now like a SQL large transfer that happened on this particular SQL box. So when we want to show this, we tried taking like Titans, like what Matt's wanted, and try to see, can we do this in the cloud security scale? So for us, like our approaches that were out there did not work because just of the volume of data that we had. And our entire goal was, can we do this not on a host level alone, but on a service level and a host level and network level together combined? So unlike the previous approaches where like the data set expertise was kind of like I could talk to folks from different buildings and understand. In Azure Sentinel, where we had to add product value, there are multiple different data sources. So obviously, first off, like Microsoft products, hooray! Like I could go talk to people when I don't know. But you know what? Customers also use AWS. That's the fact of life. And what that means, and we had to like understand how does anomalous activity in AWS logs manifest. And if you just look at like network level instances, you've got like Palo Alto, Cisco, Barracuda. So, and even when you look at endpoint, we not only just looked at Windows Defender, which we love, but also Symantec and other like CrowdStrike. So our entire like cry was, given that a customer's got so many different products, is there a way for us to stitch multiple alerts from multiple products and say some sort of cohesive story? So that is like what this case study tries to cover. So I'm first going to give you like the 50,000-foot overview, and then I'm going to drill a little bit into the detail. So the input to our system is essentially like raw events from all of these products. So, and that by itself is actually in the trillions of ranges because like each product has like a voluminous amount of just raw events. Now, those raw events get converted to like anomalous behaviors through either from an out-of-the-box alerts that comes from, say if you have like Azure Information Protection, there's like an anomalous alert that comes from there, or it could be something that we built on custom on top of that. And that also, now that's like in the billions of ranges, and which is really not actionable. So I'm going to talk in the next slide about, you've got those alerts, you've got some sort of like anomalous activities, which is really not actionable. And then we use this concept called like a probabilistic kill chain. I'm going to talk about that in just a minute. And that kind of like helps us drastically reduce the amount of security interesting cases that we want to ticket to customers. And we do one more round of scoring to kind of like only have a handful of cases. I mean, all these metrics, by the way, are for a month. So the goal of this project is not to, is not the Cheesecake Factory, where you've got like multiple assortments. This is more like an artisanal, like handcrafted, like I don't want to say hippie, but I'm Seattle, I could say that. It's customized for a particular tenant. And the expectation of this is like, it's not going to fire every day, but when it fires, it's DEFCON 1. Like, you want to put your biggest resources on top of this alert. So we really want to focus on like reducing the alert fatigue there. I know it has a lot of different drawbacks. For instance, it might like alert lesser, but we made a decision where like if we're taking time away from an analyst to look at an alert, we want it to be productive and we wanted it to be useful to them. So how does this kind of work, right? And this, by the way, is I'm going to deep dive on the third and the last two boxes. So the first thing we do is we construct a graph, and we basically take wherein the vertex is essentially an entity. It could be like a username, it could be an IP address, it could be a VM, it could be a host, doesn't matter. And the edge is any sort of like connection between them. So if ROM is logging into a VM, you should see an edge sort of like connecting between ROM, VM, and another node for IP address. And and the events for this is just like we get from Microsoft and like partner security products. Really, we haven't done anything over here other than we've constructed a graph. And this graph itself has like billions of nodes and edges, right? And what we essentially did is we wanted to prune this graph using like a probabilistic kill chain. Like what we understood by talking to analysts is that the blue team kill chain that I showed you at the beginning is a static kill chain. It assumes the attacker, after, she compromises the box, she's only going to do lateral movement, or she's going to go to the next step. It does not account for the fact that, once she compromises a box, she might compromise other boxes. So we wanted to bring an element of probability to it. And essentially, we were thinking, what does it mean to have a probabilistic part to a kill chain? And we found out that blue team folks especially, not all kill chains are kind of like treated equally, right? So for instance, like if I see an alert wherein the kill chain has progressed all the way to exfiltration, that's probably like a bigger bang for the buck than like, looking at an alert for just reconnaissance. You'll just have one step for that kill chain. So complete kill chains are preferred over like incomplete kill chains. That was like our first criteria right there. And the second thing was that we wanted to be time bound, right? If I see like an event for, say, unusual process, but if all the preceding anomalous like logins happened like 2 years back, then it's really not that interesting. But if I see like anomalous process, anomalous process, and right before that there was an alert for like a malware on the host, that's way more interesting for an analyst. So we put conditions on like time on when we pruned this graph. And we also looked for commonalities, right? Even though this is constructed in the context of a particular tenant, we wanted to see like if those kill chains manifest across different tenants of the same profile, that's probably interesting. Probably there is a campaign that's happening on a particular type of industry, which means that an analyst definitely needs to know about. So we essentially use these as priors to the graph that we constructed to essentially regularize them. So we want to prune away any sort of like uninteresting noise that's coming through the graph. And that would essentially give you, that's that step right there. So we made a decision to have one more round of like scoring because we felt that just by including domain knowledge, it's fantastic, but we also wanted to include the labels that we had from our previous cases. So we basically took features like, is this attack over different tenants, number of high impact activity across the graph, and we were able to do one more round of scoring on top of these like interesting subgraphs to reduce the noise further. So this is how it looks today. If you look at the first thing to notice is that the classification takes still in the order of hours. It's not in the order of seconds, like how the previous approaches were. We're trying to try to run that debt down. We get like billions of alerts per day, but our training time is still, for that particular volume from especially multiple data products, we are kind of gated on the throughput of those products, but we're still able to keep that within the order of hours. And I have like 5 minutes, but I'll show you a very quick demo right here. So this is like what, let me show you this. This is what like a case would look like in Azure Sentinel. So essentially like this is when there was let me show you the full details. This is when there was an anomalous login followed by a suspicious like O365 like mailbox creation rule. So for what we found in a bank was we first saw like the bank that was headquartered in the East Coast. We saw a suspicious login from Germany, which by itself is not that interesting. People travel. But subsequently, within a short period of time, we saw like that person's mailbox was forwarded to an external Gmail address, which is like super weird. And essentially what this does is that we were able to like, because this was happening like these two events from multiple different services, we were able to get them and try to stitch them together, and this is what like an analyst would see. So it's kind of like the classic, like taking those two yellow alerts, which by themselves may not be interesting, and trying to get that, that high red alert. And one of the big advantage of like having that graphical representation is to show when the user clicks an investigate button. Oh, I think like I might not be able to. So these are the two alerts. This is like the user entity, but you could get any sort of like related alerts for the user entity, because like we're pivoting, we've already have that in our graph backend. And I can switch over to timeline. Actually, let me not do that. First, let me show you this. But I can kind of like see for the user that's under investigation, all the alerts that are related for that particular user. I can also run, this is like, we're able to display this in a relatively fast fashion because it's already part of our graph backend. And for a particular entity, you can also do things like show me, let me show you this. I can get like their office activity. I can see the services that they created, the user account that's failed. So for any sort of like investigator, it kind of gives that experience from our backend when they click that big blue investigate button. So I'm going to kind of like wrap up in the interest of time so we can have questions. So the most important thing that you want to take away is, when you're protecting the cloud, you really want to think of like mind shifts, at least that we found useful, is think about the enormous volumes of data that you're having, and also think about the differences in architecture from on-premise versus the cloud. And really, there's a lot of interesting debate out there about like, can machine learning even help in cloud security? And we obviously feel very strongly and positively about it. And hopefully, we've taken away how we drove down, how we were able to increase the true positive rate, and how we were able to scale in the billions of ranges. So, I put some resources in here. I'll send the slides out. But if you have any questions, please let me know. You can always email me if you don't want to ask me, or I'll be hanging out over here. Super happy to help with all of this. Well, thank you.
So we have about 2-3 minutes left, so we could take about 3-4 questions.
So you mentioned that you were doing that probabilistic kill chain sort of subgraph or graph pruning. I'm curious if you looked at other methods, like there's the unified kill chain that leverages more like the attack matrix and stuff like that, or any gaps that you found with the kill chain, especially given that you want to weight the later stages more than those earlier stages, and other ways you would have dealt with that?
It's a great question. I think like one of the deficiencies for the attack techniques is that we did not find them mapping directly to cloud-based attacks and service-level attacks. I know that's rapidly changing. In fact, like Sharon Share from my team is working on that. But essentially, that was like our biggest deficiencies. We did not find anything cloud-based that we can directly reuse. Yeah.
So you mentioned that if a simple model works, use that. It's, you don't need to overcomplicate the problem. Yeah. But I've seen a lot of times where people who are getting started in machine learning, like they can run a model and the model produces something, but they may not know whether it was simple, or whether the simple model was good, or whether it was too good, and they've got some overfitting problem. And so how does someone who's starting out know whether the simple model is actually good?
That's a good question. Well, I think the way we kind of like convince ourselves like simple model works is just like in terms of code maintenance, like legacy code integration, like if you're able to do nothing like doing unit tests on your code, so code coverage and all of that. So you get all these like goodness by using simple models. But how do you know a simple model is good enough? Like we have like really good program managers and we get good business metrics from them. And if our system is able to meet or exceed their business metrics, checkbox. The overfitting problem, I feel like, when you're evaluating, take into consideration the diversity of your tenants. Like if all your training data was only on, say, small SMBs, but then you have to put this in production to, say, data from Fortune 500 companies. You've got data distribution disparity. I would say collect very different sort of data sets and then test them. That would be my advice. Anyway, we've got to stop, but I'm going to be hanging out outside for a couple of minutes. But I also want to attend the next talk. So yeah, I'm super happy to help, though. Thank you. Yeah, thank you.